Alright, having discussed threads and executors, let's get back to our IDE and let's talk concurrency problems. Alright, so let's illustrate our main pain point with a small method that I'm going to call run in parallel. And this is where I'm going to start making use of vars. So I'm just going to create a var x equals 0. And I'm going to write to x from two different threads. You probably know this problem. It's pretty classic. So if I create a new thread where I say x equals 1 and thread 2 equals new thread with this guy, and then I start both threads, so thread 1 start and thread 2 start, and then I print line x. Then if I try to run this, let's say 100 times, let's say for whatever in 1 to 100, then run in parallel, then you'd be surprised or not to see some various results. So x equals 0 in most of the cases, which means that the print line statement got to execute but before the threads actually ran. So no thread was actually able to set x to either equal to 1 when the print line statement was executed. But this is not always the case. So if I, for example, increase the number of runs to say 10,000 and then I run this again, I might see some different results. So I see 0 most of the time, but that's not always the case. Let me try to see if I can find, for example, a 1. So see, x can actually be 1 because at this run, at this particular one, thread 1 could run to x by the time the print line statement was executed. Let's see if I can find a 2 value as well. I can only find, all right, so most of the time the result is 0, and some of the time, which is very rare, I can actually see x equals to 1. Now, if you're already experienced, you might roll your eyes. If you're not, your spidey sense may trigger at this point that this is a serious problem. This is called a race condition, because two threads are attempting to set the same memory zone at the same time. Now, race conditions are of course bad because they can introduce bugs in multi-threaded code, and they are notoriously hard to diagnose and fix. Let's give another example which is potentially more important. Let's say we create, let's write this below the race condition. Let's write a small bank account, because we're rock stars and we design and implement critical applications. And this bank account holds an amount of dollars or pounds or whatever you want, the amount of money that a user can have. And let's, for convenience, implement a method toString, which just prints out the amount as a string. All right. And let's create a small method called buy. So the user wants to buy something out of an account. So account is a bank account. And let's say it buys a thing which is of type string, and the price which is of type int. And let's say that the implementation is something like account.amount minus equal price, which is the amount of dollars that we subtract from the user. And let's just print line, and let's make the user brag about what they've bought. So say I've bought plus thing, and let's also, for debugging or for user notifications or something like that, let's print that my account is now, and let's just print the account. All right. And let's, for the sake of testing, do the following. Let's say for whatever in 1 to 1000. So for 1000 times, let's do the following. Let's create a small account, which is a new bank account with, let's say, $50,000, which is a lot of money, and 2 threads. Let's say thread 1, which is a new thread which wants to buy from account. Let's say it wants to buy some shoes, and those shoes are $3,000. A lot of money if you ask me. And another thread which wants to buy, say, from the same account, of course. Let's say it wants to buy iPhone 12. Who knows how that's going to look like? And let's say that's going to be $4,000. Again, quite a lot of money. And let's say we start both threads. So thread 1 start, thread 2 start. And let's just sleep for a second, or for a tenth of a second, and just print line an empty line so that we can differentiate between each run. Before that, let's comment out all the other runs so that we don't get some polluted output. You comment out with command or control slash. So let's comment this out as well. And let's comment this out as well. So I'm just going to tab these out, and I should be good to go. So we have 1000 runs for this little code, which in 2 simultaneous threads from the same bank account, I'm buying shoes for $3,000 and an iPhone 12 for $4,000. And I'm curious to see how much my account is after each run. It doesn't seem I can find it because it's very, very rare, but let's write a small trick. So let's comment out these print lines. That was for debugging purposes only. And let's just say that if account.amount after the threads have finished running after the sleep is not equal to 43,000, then let's just print aha. And also let's print the actual amount. So account.amount. And let's increase the number of runs. Let's say to 10,000 or 100,000. And let's just remove or reduce the sleeping time. And let's run this a bunch of times. All right, so I have here a 46,000. So what does that mean? It means that we have 2 threads that have entered a race condition, and a user somehow managed to buy shoes and iPhone 12 and only extract $4,000 out of their bank account. So one scenario of why this could happen, say we have thread 1 which wanted to buy shoes. Thread 1 started with account with $50,000, and thread 2, which wanted to buy iPhone, started as well with $50,000. Because these things can run in parallel, this operation, account.amount minus equal price, is not atomic, so that is rewritten to account.amount equals account.amount minus price. And if the 2 threads running in parallel see the same account.amount, which is 50,000, that's a perfectly legitimate starting point. So if the thread 1 buying shoes saying account equals $50,000 minus $3,000, that's $47,000. And at the same time, the thread 2 buying iPhone says account is $50,000 minus $4,000, that's $46,000. And this guy overwrites the memory of account.amount. Then this is the final value that we see here, and we printed aha. So you see how race conditions are super bad, especially in the context of banking and financial services, because you're playing with either your money or other people's money, not sure which is actually worse. So we really need to address concurrency in race conditions. Now, fortunately, Scala and the JVM have tools for us, and we have two paths that we can take. Option 1 is to use synchronized, which is a method on reference types. Here's what I'm about to write. I'm going to write a thread safe by safe method, which has the same function signature. So say account, which is of type bank account, and a thing, which is a string, and the price, which is an int. And I'm going to implement this as account.synchronized, and watch how this method is actually written. It takes a type parameter t and a value of type t that is an expression of whatever type I want. And the property of the synchronized methods is that no two threads can evaluate the expression that I'm passing here as a parameter to synchronized at the same time. So no two threads can evaluate this at the same time. So what I'm going to say is account.amount minus equal price. And then I'm still going to print these little things, like print line that I've bought, whatever. Okay, and my account is whatever. Okay, and I'm going to pass in a little block expression so that I can put in the multiple expressions inside. And because synchronized takes a single parameter, I can use it with the syntactic sugar that we talked about at the beginning of the course. So we can say account.synchronized and then pass in a block. All right, so in this way, by synchronizing this expression on the bank account, we've managed to isolate the evaluation of this little block in between threads, in the sense that no two threads can interfere in evaluating this expression. So if I do this test here by running the same buying shoes and buying iPhone 12 on the same bank account for 10,000 or a million or a billion times, I'm not going to be seeing any more weirdness at the end. So that's option 1, synchronizing on the critical thing that's going to be modified. Option 2 is to use an annotation called @volatile. @volatile, annotated on a val or var, means that all reads and writes to it are synchronized. So an equivalent way of buying something from a bank account in a thread-safe fashion is to annotate this little var amount with @volatile. Now, of these two options, the more powerful and the more used one is the synchronized option, because it allows you to put in more expressions in the same synchronized block. So it gives you more control over what you want to synchronize and isolate in between threads. Alright, so now you know concurrency problems on the JVM and how to address them. Let's do some exercises. 1. I want you to construct 50 inception threads. Inception threads are threads that construct other threads. So thread 1 constructs thread 2, constructs thread 3, and so on and so forth. And I want every thread to say print line hello from thread whatever number I am. All right, and I want you to print these greetings from the inception threads in reverse order. So think about how you would do that. All right, this is simple recursive function, but I want you to order the threads in a particular way, and this will practice the start and join methods. All right, cool. Exercise number 2. I have the following code. Let's say I have, let's put this in a separate comment. So I have exercise number 2, and I have the following code. Let's say I have a var x equals 0 and some threads, which is 1 to 100, map, and for every index, I just create a new thread. And this thread will just say x plus equals 1. So each thread will attempt to increment the value for x. All right, and I'm going to start all the threads, like threads for each start. Now my question is, I actually have 2 questions. One, what is the biggest value possible for x? This should be pretty easy, but the next question is not so trivial, and that is, what is the smallest value possible for x? And the third exercise is again on a piece of code, and this is called the sleep fallacy. And let's say I have a var called message, which is starting from an empty string. And I create an awesome thread, which is a new thread with a new runnable, which does the following. It tries to sleep, and then to set a message. Say Scala is awesome. All right. And in the main thread, I'm going to say message equals Scala sucks, and then start awesome thread, and then I'm going to sleep for, say, 2 seconds, and then I print my innocent message. And now my question is, what's the value for message? Is it guaranteed? Why or why not? All right, so take a second to think about these exercises, try to implement them yourself, and I'll come back with solutions and explanations in just a few moments. All right, so I hope you implemented at least the first method, the inception threads. This is pretty cute, and the other 2, I hope you at least thought about them. We're just going to go through them in turn. So for the exercise number 1, let's call a method called inception threads, and let's give a parameter of, let's say, max threads, and an index, which is an int, and let's say the default parameter is 1, and this will construct a thread. Okay, so the result of this inception threads method is going to be a single thread, which will then start some other threads. Okay, so this is a new thread with a new runnable that does the following thing. If the index of this thread is less than max threads, then I'm going to do the following. I'm going to create a new thread, which is the recursive call of inception threads with the same max threads parameter and i+1, the new index. And then I'm going to start it. So new thread dot start. Then I'm going to wait for it to finish. And after the new thread has finished, so after the inception thread has finished printing hello from thread 1, 2, 3, 4, 5, 6, 7, 8, whatever, 29, and I'm thread number 30, then I'm going to print line my own message. So let's say hello from thread I. So this is the index of the current thread. All right, so this should be it. So if I run inception threads with 50 threads, And then I hit the start method. Let's right click and run this. Actually, let's kill these runs because they will pollute our they will pollute our system out. Okay, so we should be good now. If I run this, we have the hello from thread 1, 2, 3, 4, 5, 6, 50 in reverse order as expected. All right, so this is basically a stack recursive call, and the new threads are started and joined before the current thread has the chance to say hello. Okay? All right, so exercise number 2. So we basically have 100 threads that want to increment a variable. So the best case and the biggest value possible for x occurs when all these threads act sequentially. That is, all the threads increment x in turn. So the biggest possible value for x is, of course, 100. So this was pretty easy. Now, the smallest possible value for x is actually 1. That's because, for all we know, threads act in parallel, so all of them can do the following. Thread 1 reads x equals 0, and so on and so forth. Wow, I can't do suspension points here. So we can have thread 100 also read x equals 0, and all of them attempt to say x equals 1 and write it back. So for all threads. So for all we know, all the threads might read x equals 0 at the same time, and all the threads might write x equals 1 at the same time. So the minimum possible value for x is actually 1. This occurs very, 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 very rarely, but if you try to run this multiple times, so start 100 threads and print x, most surely you will not see always 100. You might see any number between 1 and 100. So just for a test toy code, if we say threads for each join, so we're joining all the threads, and then I'm printing x, I might see any number between 1 and 100. Most of the times I'm going to see 100 because the operation of getting a setting of value for a primitive value such as an int is very quick, but that's not guaranteed. So as you see here, I have a value for 99, not 100. So one of the threads lagged behind and got overridden by some other thread. In theory, you can have any number between 1 and 100 as a value for x. Very rarely, but you can. So the 99 was rare enough, 98 is even more rare, and so on and so forth up to x equals 1. But 1 in a billion trillion times, it's possible that x could have the value for 1. So be very, very, very careful. And that will bring me to exercise number 3 with the sleep fallacy. And the sleep fallacy basically describes the very, very, very wrong programming practice of synchronizing threads by putting them to sleep different times. This was, I don't know how much it still is used in the JavaScript world with all those set timeout functions, but this is a very wrong programming practice because if you put a thread to sleep for a second and another thread to sleep for 2 seconds, then does not mean that the operations would be executed in that order. So to answer the question, the value of message is almost always going to be Scala is awesome. But it is not guaranteed. And why not? Because for all we know, the execution might go like this. Let's say the main thread says message equals Scala sucks. All right, and calls awesome thread dot start, and then sleep, which relieves execution, right? So this frees the CPU to execute some other thread at the discretion of the operating system. Now, let's say the awesome thread gets the CPU and does sleep, which also relieves execution. And at this point, the operating system is free to choose some running thread on the operating system. So let's say the operating system gives the CPU to some important thread, which takes the CPU more than 2 seconds. All right. Now, after the important thread has finished running, the OS is very generous and gets back to our little program. But at this point, both the main thread and the sleeping thread, the awesome thread, have finished sleeping. So the OS is free to choose which thread to run, and OS gives the CPU back to the main thread, not to the awesome thread, which prints line Scala sucks, because the awesome thread has not modified the message yet. And after that, OS gives the CPU to awesome thread, and message becomes Scala is awesome. But by this point, it's too late because the print line statement has already finished executing. All right, so what have we learned? First, that sleeping does not guarantee that a thread will sleep exactly that number of milliseconds. It will just yield the execution of the CPU to the operating system for at least that number of milliseconds. And as we know, the operating system is a busy man or woman or thing and has a lot of things to do. And when it gets back to our awesome thread, we are only guaranteed that our thread has slept for at least the number of milliseconds that we told it. Second lesson is very simple, and it's that sleeping does not guarantee the ordering of evaluation of some expressions. We can actually prove this by changing the sleep from, let's say, 2000 to 1001, so like a smaller time difference, so that the OS can have time in 1 millisecond to schedule threads differently than we might expect. So we print Scala is awesome, but it's not guaranteed. As you see here, we can also print Scala sucks. So let's ask a bonus question. How do we fix this? Now, what's likely to pop in your head right off the bat is synchronizing, but synchronizing doesn't work here. That's because synchronizing only works or is only useful for concurrent modifications. So if two threads are attempting to modify this message at the same time, then synchronizing can work, as was the case for the bank account, where multiple threads would attempt to access the same account at the same time. But here we have a sequential problem. And the only solution is to have threads join. So before you print message, you say thread or awesome thread dot join. So basically wait for the awesome thread to join. Even if you're sleeping more than the awesome thread, you just make sure that the awesome thread has finished before you print line the message. So even if you sleep like 1001 or even less, you are sure that the awesome thread had the chance to run and modify your Scala is awesome. Alright, so what have we learned from the past couple of videos? We learned how to operate with JVM threads. We learned what they are, how to build them by passing either proper runnables or runnables converted from lambdas, how to start and how to join JVM threads. We also learned of a cute way of evaluating things in parallel without managing threads explicitly with the help of executors and thread pools, and we explored their basic API. And then we saw how multi-threaded programs can cause problems and how we can solve them with the synchronized method and with the @volatile annotation. We also worked on some exercises and debunked a common misconception about thread sequencing by sleeping. We've learned a ton. I'm Daniel, and I'm waiting for you in the next lesson where we discuss inter-thread JVM communication. So see you there.